Let's try to describe, and I will say only describe so far, not predict, but describe the different types of geometries and isomerisms that exist for coordination compounds. There's many different types of structures that coordination compounds can adopt. However, we will in this course study only four different types: the linear, the tetrahedral, square planar, and octahedral. And as you can well imagine, there's only these two cases in which you have the same number of ligands, but they are adopted and they adopt a different geometry. We will use the theory called crystal field theory to explain why it is that different metals, different coordination compounds adopt different geometries, but it's not the time yet. So far in this video we're going to describe the different types of geometry and isomerisms. So talking about um, seeing geometries, you may want to click on this link, which leads to this fabulous website that Bob Hansen wrote it's in Olive College, and you can just click on the metal and see the types of metal complexes that you will see. So one of the structures that you will not see, because it's not here, is a pentacoordinate. Okay, a pentacoordinate is a bipyramid trigonal or trigonal bipyramid. So that's one of the, it's also fairly common, but it's not in the slide because we didn't have any coordination 5. But typically, if you will, some nickel will have tetrahedral. Let's see if you click here and you can see. So I encourage you to click on that link and browse a little bit different kinds of metal complexes that you can see their structure. Sometimes it's hard to, not all of them are metal complexes, but definitely chromium X carbon monoxide. So this is octahedral in here. Okay, so please go ahead and click on that link. So talking about isomerism, an isomer is when you have two compounds at least that have the same formula but they have different structures, and it can have a different structure depending on if it's the connectivity or if it's the orientation in the space or where those different components of your formula exist. So there are 4 different cases of isomerism in metal complexes that we will study one by one. So first, let's study the first 3, which are the easiest to understand. The first type of isomerism is called coordination isomerism, in which even though it has the same components, in this case bromium is the counterion and sulfate is a ligand, but in here bromium is the ligand and sulfate is the counterion. These two compounds have the same formula, not in the same sequence, but they have the same composition, but as you can well imagine, very different physical properties, because it's not the same to have a sulfate or to have a bromium connected to that metal. There is a linkage type of isomerism that is only present when the same ligand offers a possibility to have different points of contact. So this nitro group can bind to the metal through the nitrogen, or it can bind to the metal through oxygen. So even though the formula will be the same, the properties or the color, as you can see here, will be different. And notice that this linkage isomerism is hard to show in the formula. It's not easy to tell apart. So there are some ways to say to what is the atom connected to the metal that we will not study here. And the other one is disposition in the space. So in this case, if you pay some attention, look that there is 2 chlorines on both cases, but in this one we say that chlorines are in cis, and in here chlorines are in trans. So they are not, they have the same connectivity, but they have different geometrical disposition, so they are geometry isomers. Okay, so let me give you some more examples of these geometry isomers. As we saw, there is the cis-trans kind of geometry isomerism. This one is cis, this one is trans. And let me remind you, this is the the square planar. If you want to see the square planar in 3D, well, that's what a square planar is. It can have a cis or trans, and also the octahedral, as you saw in the previous example. This one is a cis isomer, this one is a trans isomer. When you have for the octahedral coordination compounds, you can have a FAC-MER. That's a facial, comes from facial or meridional types of isomer. They're still geometry isomerisms. This position in the space, it's called facial because all the three ligands are on the same phase, if you will, of the octahedral. These are meridional because they cross the complex. Notice that if this one is facial also, there is a phase in here with the ligands. Okay, so hopefully it's not too hard to tell apart these two kinds of geometry isomers. Okay, I encourage you again to click on all of these links. It gives you more examples. If you have a hard time to visualize them in these static pictures, feel free to click on these links. It will give you examples of facial and meridional isomers or cis and trans isomers. You are expected to recognize them once you see them. Now, the last kind of isomerism, it's not straightforward because it's optical isomerism, and here's a link. And these two metal complexes, they are both triethylenediamine cobalt, that is cobalt, and 3 ethylenediamines. You can see the ethylenediamine in here. There's 2 carbons and 2 nitrogens. However, if you try to superimpose them, you will see these are not facial or meridional isomers because there's only 2 ligands in here. But if you can see here, I'm paying attention to this, follow the mouse, ethylenediamine, which is in the same side in here. But notice that doesn't matter how you spin this complex, this ethylenediamine is not in the same place. So these are actually mirror images of each other. They are chiral compounds, and what we call them, they are optical isomers. Okay, so there will be either S or R, but you do not have to identify which one is which, but it's typical when you have a bidentate, at least kind of ligand. Okay, so what we said, it's called optical isomerism. So let's finish this video with a simple exercise. So let's see what is the relationship between the following 2 square planar, and that's important, complex ions. Are they linkage? Are they coordination isomers? Are they geometry? Are they optical? If you notice, so you may want to spin this, but if you flip this, you will see, because they are all in the same plane. Okay, they are all in the same plane. I don't know how to represent this. Okay, and this is a little thinner in the back. Okay, this is, if I rotate this complex in this direction, I will have fluorine, iodine, chlorine, and bromine, which is the same as this one. Okay, this would not be the case if it were tetrahedral, but because it's square planar, they are the same compounds. It just takes some practice, okay, and we'll provide more examples for you to practice, but in this case, these 2 compounds, the way they're drawn here, are the same compound.